Welcome to the Scientific Sense podcast, where we explore emerging ideas from science, policy, economics, and technology. My name is Gil Eapen. We talk with world's leading academics and experts about their recent research or general areas of topical interest. Scientific Sense is an unstructured conversation with no agenda or preparation. We cover a wide variety of domains where new discoveries are made and new technologies are developed on a daily basis. We are most interested in how new ideas affect society and help educate the world how to pursue a rewarding and enjoyable life rooted in science, logic, and information. We seek knowledge without boundaries or constraints and provide unedited content of conversations with researchers and leaders who love what they do. A companion blog to this podcast can be found at scientificsense.com, and this podcast is available on over a dozen platforms and directly at scientificsense.net. If you have suggestions for topics, guests, and other ideas, please send them to info@scientificsense.com, and I can be reached at gil@eapen.info. My guest today is Professor Michel Janssen, who is a professor in the program in the History of Science, Technology, and Medicine and School of Physics and Astronomy in the University of Minnesota. Welcome, Michel.
Thank you. Thank you, Gil.
Sure. Yeah. So you have a very unique background. You teach both the history of physics as well as some fairly high-level courses in physics, including quantum mechanics. I want to start, kind of get a big picture view of the history of quantum mechanics, which is a field that has been around for a while. And I was just reading about it a little bit today, and I realized that the double slit experiment was in 1801.
Mm-hmm.
So that is sort of, one could argue that is sort of the start of the problem, so to speak, right? You want to give a sort of a sketch of the history of how it evolved over time?
Sure. So I should first say that so it is a bit unusual for like a historian of science to be in a physics department. That's like what is known as the Minnesota model, and so I really only teach like history of science classes, but I do a lot of guest lecturing for my colleagues in physics. So that's where I talk to students in quantum mechanics or in relativity about this kind of stuff. So now on the history of quantum mechanics, I'm actually working on a book, a 2-volume book on the genesis of quantum mechanics, together with a particle physicist at the University of Pittsburgh named Tony Duncan. And so our story, doesn't really begin with the double slit experiment, and I'll explain later like why I don't like that as a starting point. It really starts. Okay. It really starts with attempts to come to terms with something called black body radiation, which is a particular kind of heat radiation, and so it's in that context that around 1900, like Planck, to come up with a law for black body radiation is going to have to introduce this idea that the energy of resonators, like interacting with this radiation, that the energy of these resonators is quantized, that it can only take on like certain discrete values. And there's a big debate among historians how seriously he took that quantization, but let's leave that aside for the moment. The point I want to make.
So just a quick question. So that realization, did that happen experimentally, or it was sort of theoretical?
It was
insight?
So people were so basically the idea. So you have this heat radiation, and in the by the middle of the 19th century, physicists had figured out. This is like people like Kirchhoff on the basis of thermodynamics, that the spectral distribution of that radiation should always be the same. So by spectral distribution, I simply mean like how much energy output do you have at all these different frequencies. And so the challenge now was to come up with an explicit formula to give like this spectral distribution. And this is what Planck supplied. And but in order to get the formula in order to get to be able to derive the formula, which he had initially just kind of guessed, in order to derive the formula, he discovered that he had to assume sort of this strange behavior of the energy of like resonators, like that you can think of as little charges on springs interacting with this radiation. And so, and Planck was very reluctant to give too much sort of physical meaning to this. He thought in the end this was kind of a mathematical trick. Others, in particular, like Albert Einstein and Paul Ehrenfest, were taking this more seriously. And so Einstein is really the in my view, the person who sort of put this whole quantum idea on the map in 1905, where he went as far as saying like even the radiation itself is quantized and comes in little packages like that he called light quantum that are now called photons.
That's interesting. Yeah, so we don't typically think about Einstein as sort of the early physicist in the quantum physics area. And this equation, that Planck's equation, is on the surface very simple. E equal to hv, where h is the Planck's constant and v is the frequency of the radiation, right? Yeah. Mu. Okay. H mu.
Yeah.
Oh, nu. Okay.
The Greek letter. Yeah.
So that Planck's constant, and so it's a very elegant idea. And so you were saying this appealed to Albert Einstein, and he developed some of these ideas forward.
Yeah, like so what Einstein realized is that if you don't introduce this quantization idea, that classical theory really leads to problems and cannot account for this phenomenon of black body radiation. So this is something that is very famous, like that Ehrenfest called the ultraviolet catastrophe, that the energy, instead of like having a nice distribution of the energy over all the frequencies, like if you go to larger frequencies, the energy just goes up like to infinity. So what I want to say is that so Einstein saw like, okay, you can get this. The way to think about like radiation is in terms of these little packages, right? And so the energy of like a photon is that same equation you mentioned, E equals h nu. And then like 2 years later, so this was not a popular idea. People, like a lot of people resisted this, Planck included. And so 2 years later, like he came up with the idea, like, okay, I can use that same sort of quantization idea to tackle like another problem that people had run into in the 19th century, not black body radiation, but the specific heats of solids at low temperatures. So the expectation was that the specific heat is just the same at all temperatures, right? So the specific heat is like how much heat do you have to add to a particular substance to like make it rise in temperature by 1 degree, and that depends on what kind of substance you're talking about.
So is it correct to think about this, Michel, as sort of a transition from the analog way of thinking about it to a digital way of thinking about it, or that is not?
For this early phase, you can certainly think about it that way, right? So, but in a way, like so this gets to the question, like what is distinctive about quantum mechanics as opposed to classical mechanics? And the initial idea you may have, and which the name quantum mechanics suggests, is that, well, classically everything is like continuous, and like in quantum mechanics everything is discrete. That turns out not to be the case. But like early on, that definitely seemed to be sort of the hallmark of quantum theory, and hence the name. So Einstein now had these two different applications for these quantum ideas, and those ideas are really typical of the early development. And so people often ask me, like, when did quantum mechanics get started? And so physicists like to say, well, it was with Planck in 1900. Well, but I'm thinking like, well, but Planck wasn't taking these ideas too seriously. Well, what about Einstein in 1905? Okay, well, he was taking it seriously, but very few others were. I think a better starting point is the first big conference devoted to quantum mechanics, which was in Brussels, the first Solvay conference in 1911.
Yeah.
And there, like, there's a famous picture of all the physicists that were invited. And in the background, you see like a blackboard with Planck's formula for black body radiation, and then you see like a little a sheet of paper with some graphs for the specific heats of solids. And those really were the two topics. And in both cases, what you're talking about is really a form of statistical mechanics where you look at the collective behavior of large amounts of very simple systems, like, called harmonic oscillators. Now, the big game changer in the history of quantum mechanics comes in 1913 with the Bohr model.
Yeah.
So now all of a sudden, like,
right.
I think your listeners, like, we've all seen this in high school, right? You think of atoms as like little solar systems where the electrons go around the nucleus like planets around the sun, with the difference that only certain orbits are allowed. And that was really a game changer, because now all of a sudden quantum is not anymore, it's no longer about the collective behavior of these very simple systems, but trying to model individual and sometimes quite complicated systems like atoms with like, one or more electrons, atoms put like in a combination of electric and magnetic fields. And people are now trying to account for a wealth of data coming out of spectroscopy, because they knew that, these atoms and these molecules, they all have very characteristic spectra, but there was absolutely people had no idea how to account for any of this. So what Bohr supplied was, well, at least we now have a prayer to come up with a theory for the structure of these atoms that can explain like why we see the light given off by the atoms having the frequencies they have. So this, yeah.
And so this was sort of a necessary condition, because electrons could only occupy certain energy levels, right? So they just couldn't have gotten this model without that idea.
Yeah. So this basic idea of this energy is quantized, that really fed into Bohr's thinking. But like what Planck and Einstein had not considered was to now really think about like models of atoms. And this really came, so there's experiments done by Rutherford. So Bohr, of course, was Danish, but he did this work while he was in Manchester as a postdoc with Rutherford. And Rutherford did these experiments like showing that, the structure of an atom is like, it's a nuclear structure. There's something, most of the mass is in the center, and then you have electrons whirling around it. And what Bohr did was make a more precise model of that basic idea. And for about 10 years, people started, kept working at this. Bohr, and in particular, like his colleague in Munich, Arnold Sommerfeld, and two of Sommerfeld's students who became household names, Wolfgang Pauli and Werner Heisenberg, trying to like work out these ideas. And by the early 20s, they had some success early on, but by the early 20s, it was mainly misery. They could not. They could like come up with like all kinds of empirical rules for like spectra under like all sorts of conditions, magnetic fields, electric fields, Zeeman effect, Stark effect, but they could not come up with like consistent mechanical models that would explain these rules. And so then like there was this move like in the mid-20s. Yeah.
So during that time, 1910 through 1920. Einstein's theories are developing simultaneously, right? Obviously, a different field altogether, but that's
Einstein Einstein did very important work early on quantum, like on black body radiation, on specific heats, till about like 1911, and then like he got frustrated by quantum theory and spent the next 6 years or so working on gravity, right? And so like he produces his general theory of relativity. And after that's done, like in 1916, 1917, he returns to quantum theory, but now Bohr has arrived on the scene. And it's actually Einstein who sort of picks up on some of these ideas of Bohr And so what we teach our students in high school is really a mix of Einstein's ideas and Bohr's ideas. So Bohr, for instance, hated the idea that when an electron jumps from like one orbit to another orbit, that a photon is being sent out. He thought a classical wave was being sent out. No, said Einstein, it's a photon. And that idea was not accepted until the early 20s. So what you get then in the 20s is that people like Heisenberg and Pauli, just to mention the most famous names, there's with help from people in Göttingen, a center for mathematics, with Max Born, his student Pascal Jordan, they developed this very abstract kind of mechanics that becomes known as matrix mechanics, where you just completely give up the idea that there are these well-defined orbits. Okay, so that's one path to that's in fact sort of the main path to quantum mechanics. Now, the ideas I was talking about earlier about the collective behavior of very simple systems and a kind of statistical mechanics, that doesn't die. That is picked up again in the early 20s by other like big names like Louis de Broglie in Paris, Bose like in Dhaka now, right, and so Indian physicist, Einstein himself, and in the end Schrödinger, and that then leads to like a completely different form of quantum theory known as wave mechanics, right? So in 23, 24, like there is this period of, well, there's nothing that can account for what we're seeing here. And then by 26, you all of a sudden you have like sort of an embarrassment of riches that there is like at least two different theories that look completely different that can account for the phenomenon. And there's Dirac.
So matrix mechanics and wave mechanics. So these are the two kind of dueling theories to sort of explain
and
quantum.
So now like there is a variation on matrix mechanics due to the British physicist Paul Dirac called Q number theory. And so like all of a sudden, like by 26, there's these different theories floating around, and people are trying to sort of make sense of like how they relate to each other. So Schrödinger and Pauli realized early on that although these theories look completely different, they always lead to the same prediction. And so then Max Born realizes, well, these theories are also statistical theories, which is sort of a novelty, right? In physics, it's about probabilities. And then, like in very short order, in late 26, early 27, Dirac and Jordan, two of the pioneers of these fields. I should also mention the people that I'm mentioning here are incredibly young. Like they're born around 1900. If you look at the picture that at that Solvay conference in 1911. None of them are there. No Dirac, no Heisenberg, no Pauli, because all these guys, they're teenagers. Like at that point, the fifth Solvay conference, the famous one in 1927. There you see like Heisenberg and Pauli, and there the champs of 1911 like Planck and Einstein actually already look quite old. So things are moving very fast, and so Dirac and Jordan in late 26, early 27. Come up with a formalism that unifies these two theories. This is called like statistical transformation theory. And then, like shortly thereafter, the Hungarian, later American mathematician John von Neumann, reading some of Jordan's papers, he thinks like, my goodness, I mean, these guys don't know like some mathematics that mathematicians have known about for 20 years. And I can actually do this unification of these two theories in a much more elegant fashion using some of these mathematical ideas that he then calls like Hilbert space, right? So this is
Now, Fermi on the scene also during that time.
Fermi is like he comes a little bit later. So I would say Fermi is more the further development of the theory. So. Of course, if you hear like Fermi, you think like fermions and bosons, and bosons, of course, named after Bose. And what this is like Bose-Einstein statistics. It's about like how to do the statistical mechanics of large collections of simple systems. And so Fermi, so opposed to Bose-Einstein statistics, you have Fermi-Dirac statistics. where you can do some like similar things for now particles with spin. Like, so this is another element that comes out of left field in the early 20s, like the discovery of electron spin. So this is, I'm originally from the Netherlands, as you can probably tell from my accent.
Yeah.
And so I can with great authority pronounce the names of the two people who introduced that. That's Goudsmit,
Yeah.
Goudsmit and Ulembeck.
Yeah.
But in order to really do that properly, you need to further develop quantum mechanics into like something called relativistic quantum mechanics, which will become what we now call quantum field theory. And it's more in that context that I think that people like Fermi become important. Like the heroes of like the sort of the early establishment of non-relativistic quantum mechanics are the people I mentioned, right? So on the matrix mechanics side, you have Heisenberg, Born, Bohr, Pauli, Jordan, and on the wave mechanics side, you have de Broglie, Einstein, and Schrödinger and Bose.
So during this time, there is some sort of not a conflict, but disagreements, right, between Einstein and the proponents of quantum mechanics.
Well, that again comes a little bit later, right? The big conflict at this point is the conflict between the people in the matrix mechanics camps and the people in the wave mechanics camp, right? And so Heisenberg is on record calling like wave mechanics disgusting, and Schrödinger, not to be outdone, is calling Heisenberg's matrix mechanics repulsive, or like terms of that effect. But so what I find interesting, and I hope we get to this later, is that these two theories are really quite different, and they have sort of different roots in the earlier history, and that gets papered over by the fact that within a year or so it was shown that these two theories are just mathematically different descriptions of the same underlying situation. But to this day, I would argue, you can see that people think differently about quantum mechanics, depending on whether they are sympathetic to the sort of Schrödinger line of thinking, or whether they're sympathetic to the Heisenberg Bohr line of thinking. Right?
So from your perspective, Michel, so what would you think is more simple and more elegant, if they are ultimately describing the same process?
Okay, that's an interesting. So I would say without hesitation, matrix mechanics, but that goes very much against the grain of like what is accepted physics. So if you look at how the theory was disseminated, and in particular like how it was turned into textbook physics, it was like a slam dunk victory for wave mechanics. And people were very, and I think that's just partly because the physics community in the mid-20s was very accustomed to using the kind of mathematical techniques that you need in wave mechanics. People were very, proficient in like dealing with like wave equations. The kind of mathematics that you need to do matrix mechanics, like we now call linear algebra, was far less familiar. I mean, like Heisenberg himself did not, when he first published his paper and is basically looking at matrices, he did not recognize that. He had like, well, there's this strange thing that there are these objects that are central to my theory that have two indices, one indicating an initial state, one a final state, and if I have two of these objects, column A and B, they do not commute. A times B is not the same as B times A. Now, that's, of course, a standard property of matrices, but it had to be pointed out to him by Max Born, with whom he then wrote another paper, that was indeed like a very well known like mathematical object. So these techniques were unfamiliar to physicists. And another thing that illustrates that is that it took like a mathematician like von Neumann to instruct physicists like, okay, this wave mechanics is just one particular way of doing business here, but you can also do business like the way that the matrix mechanics people are doing. And so the reason I say like I prefer matrix mechanics is that it's sort of a more austere picture of the situation. Like if you go for wave mechanics, it's very easy for all kinds of like imagery coming from waves to slip in. So actually, this is nice because this is precisely why I don't like to start with like the double slit experiment, right? Because right. So if you have so the way I think about the in quantum mechanics, the double slit experiment is like, okay, the statistics that you get if you do like measurements are going to depend on like what you do to the system, whether you send it to one slit or to two slits, and so that's just the hard experimental facts. And if you then like start like embellishing that story about like, well, you should think of this electron as like a wave that goes through like both of these slits, well, you're introducing some imagery that may actually be quite misleading, right? So for starters, these waves are not waves in ordinary space, right? I mean, that works if you have one particle, but if you have two particles, they're already waves like in 6-dimensional space. So they're waves in configuration space, and like as Born like pointed out to Schrödinger initially thought these are like very physical waves, right? But Schrödinger is presenting these ideas in early 26, and by the end of 26, Max Born has already convinced him, like, no, these are at the end of the day, they're these are waves in these higher dimensional spaces, and they have like a probabilistic interpretation.
So are there some experiments going on in parallel? These are all sort of theoretical.
So I'm mostly interested in the history of theoretical physics, but it's a good question. I'm glad you asked this because, like, yes, there are incredibly important experimental developments. So remember, I started with like it's all about black body radiation. It was because of precision measurement of these curves for black body radiation in the late 1890s, but people now completely forgotten, like Lume, Pringsheim, Rubens, Kuhlbaum. I mean, they if they had not done these precision measurements, like a law that was derived before Planck by Wien would have done just fine. It was that people were really trying to do this very precisely that Planck realized that Wien law is wrong, and I need to come up with something else. So that's one. One of my colleagues in history of physics, like Alan Franklin, who is a specialist on the history of experimental physics, right? He wrote a book, The Neglect of Experiment, calling out precisely the bias that you're pointing to, that historians of physics, myself included, tend to look at theory rather than experiment. And in Neglect of Experiment, let me just like this is a good anecdote. He's using like Shakespeare and Stoppard and saying like, the announcement that to a group of physicists that Lume and Pringsheim are dead is like, like people in Hamlet being told that Rosencrantz and Guildenstern are dead. Like, who cares?
But at this juncture, though, the theory is getting accepted. It's sort of the mechanics of how it works that is being debated. Right. So but
let me. I'll keep it short. But there's a lot more to be said about the experimental side of things. So it really, I mean, if you look at the period from 1913 to 1923, I mean, there's so much information that they didn't have about spectroscopy that becomes available. And in a way, it's lucky that early on the data are very imprecise, because that means that you can get away with murder, essentially, like theoretically. But by the early 20s, like the experimentalists have nailed down so many of these parameters, and like some of these spectra are so well known that they really are a great testing ground for like these models. And that's when it becomes clear that these in hindsight, very simplistic models of sort of miniature solar systems are just never going to work, and that drastic steps are required, either to abandon this whole idea of orbits. That's what Heisenberg and co. do in matrix mechanics, or to just give up the idea that we're talking about particles and thinking like really it's sort of a wave phenomenon, which is the path that Schrödinger then takes. So yes, these experimental developments are extremely important. Without those, nobody would have seriously considered like adopting a theory that is as weird as quantum mechanics.
Okay, so maybe we'll take a quick break, Michel, and when we come back, we'll talk about the 30s and beyond. Okay, talk to you.
This is a Scientific Sense podcast providing unscripted conversations with leading academics and researchers on a variety of topics. If you'd like to sponsor this podcast, please reach out to info@scientificsense.com.
So we are back. So we were just talking about, Michel, about the quantum mechanics, the development, the people involved from 1900 to 1930 or so. So by then, the field is getting reasonably well established, right? Is it I think that the textbook, The Principles of Quantum Mechanics, came out somewhere around the 1930s?
Yeah, that's true. So there's there's several books coming out on basically presenting mostly sort of a wave mechanics, the wave mechanics point of view on quantum mechanics.
Okay. And so at that point, how has it progressed from that point on, and who are the major characters?
Okay, so like in physics itself, what you're seeing is that this theory is going to be applied to like other fields, right? So as I was telling you before, like it very much comes out of like atomic physics, but like going into the 30s, they're going to probe deeper, and they're going to look at nuclear physics, like looking at the structure of the nucleus, and also at like collective behavior. So this is like when it's going to be applied to things like solid state physics, right? And leading to important. So nuclear physics, of course, in the end is going to lead to atomic bombs,
right?
And condensed, or like solid state physics, now called condensed matter physics. I mean, that's going to like result in something like transistors, right? So there's very important developments within physics. And so quantum mechanics is like unbelievably successful. It's clear that this is not just like a theory atomic physics. It's really like a whole new way, a whole new framework of doing all kinds of physics, right? And so today, the only thing that has not been brought under its purview is gravity. And everything else is governed by the basic principles of quantum mechanics. And so I like an analogy from computer scientists where they're saying like, look, quantum mechanics is just a new operating system. And like all these different applications, atomic physics, molecular physics, condensed matter physics, they're all different applications, like written for that same operating system.
It's a complex operating system.
Very complex. Though I mean, yes and no. Yeah. So if you follow like the historical development, like it's unbelievably hairy and complicated. But what is surprising to me, so as a professional historian of physics, what I find surprising is like it's unbelievably complicated to understand like all the fine points of the spectroscopy that got us to quantum mechanics. But once you have the theory and once you present it like in a simple form, like von Neumann did, it becomes unbelievably simple. And so if you now like are interested in applications in quantum information, you don't have to worry at all about like all these complexities, and you basically get by with learning just a smidgen of linear algebra, and you're off to the race.
Yeah, it has high predictability, and hence plethora of real applications coming out of it. But I often hear, Michel, that at the heart of it still have difficulties. We can't really describe in highly intuitive fashion how it works, right?
Yeah. No, this is you hit upon like the big problem, of course. So in like it on the one hand, it's clear that this is tremendously successful in terms of like doing physics. On the other hand, like it's very unclear like what to make of it. And like, so, all right, so we can, we can calculate like all these, we can predict the outcomes of all these experiments. But what does this tell us about like the quantum world? What is this world like? And that is a debate that started as soon as the theory was born, like in 25, 27. 27 in particular, when you have like the fifth Solvay meeting, you have the Como conference, you have like the first clashes between Einstein and Bohr, like very famous. And that debate essentially continues like unabated to this day, right? So there was like a period of decades where like the mainstream like was exerting like like great control over what people were allowed to think about this, right? This was the period that the physicist David Merman has described as "shut up and calculate." And but then like in the I would date it to like the late 80s, early 90s. People were dissatisfied with these answers that were supposedly given by Bohr in these very hard to read papers and very woolly formulations and all this. And so now like there's sort of a plethora of like different interpretations on the table with very serious defenders, like ranging from like the Everett many worlds interpretation, Bohm.
So before we get into so what was Einstein's problem with it? Well,
so Einstein,
Okay,
so Einstein, of course, Einstein's most famous one-liner on quantum mechanics is "God does not play dice." And so I don't think, I mean, the statistical nature of the theory, I don't think this is what bothered Einstein like most about it. So the thing that bothered, so there's a few things that bothered him, right? So one of the things is like like that something that for which Schrödinger like introduced the name entanglement. That like in quantum mechanics, things have this tendency to get sort of entwined with one another, so that you have like a compound system consisting of two components, and you can no longer assign like a separate states to these two components. Like you can only ascribe a state to the compound. And Einstein thought, well, if you can't do that, we can't do physics as we know it anymore, because we're always talking about, well, what are you doing to this particular system over here, and that should be independent of what you're doing to like a system like over there. And what we seem to have in quantum mechanics, as he once put it, is that we seem to have sort of spooky action at a distance, that when I do something over here, that immediately starts to affect something over there. Right?
So this is like if you have two particles, let's say two electrons or something, and if they're entangled, then if we observe electron one, then you some property of electron one, let's say spin or something like that, then you automatically know what is the property of the second particle, right? Regardless of the distance.
Correct.
Between them.
Yeah.
And it's very counterintuitive, because we were all taught that information cannot travel more than the speed of light. And so conceptually you can separate these two particles to the both sides of the universe, so to speak, but they will immediately have that type of it's not necessarily information exchange, but that's a paradox. Right?
No, so but what's weird about it is that you measure the spin of one particle, like, so you have like an entangled pair of particles, where entangled just means like like it's described by a state that doesn't sort of factorize in the state of one particle, state of another particle. Now you let these particles separate, you measure the spin in one direction of one particle, or like the polarization of a photon on one photon, and the spin in another direction on the other particle, or the polarization, and these things are very strongly correlated, right? But what quantum mechanics also shows is that those correlations can never ever be used to send signals, right? So in the foundations literature, it's now like you always have the same characters. It's always Alice and Bob, performing these measurements. And so, the first step is to realize, whenever Alice like finds up, Bob finds down, and vice versa. That's very strange. And then the next statement is, but Alice and Bob cannot use that strange behavior to send each other like instant messages.
Right. Right.
And so there's different ways to think about this, and this is like what the debate, like in the end, is it has been about for decades now, right?
Right. And so people came up with so let me understand that, Michel. So if Alice is down, Bob is up, and vice versa, and that is regardless of the separation between them.
Correct.
But we say you cannot use that for information exchange, and why is that?
Well, I mean, like if you look more carefully at the mathematics of these correlations, you see that like what would you have to like imagine what it would be like to try to exploit this for communication purposes.
Yeah.
Right? So it's like, in the end, it's like 50-50 if you do a measurement of spin in a certain direction, whether it's going to be up or down. But these correlations also persist if you also have these correlations if you measure spin in one direction, Alice measures spin in one direction, and Bob measures the spin in some other direction. Okay. And so now, like, imagine that they make a plan together and say, okay, you're going to send me the answer to a simple yes/no question, and if it's going to be yes, you're going to measure spin in the x direction. If it's no, you're going to measure spin in the z direction. And then you do that, Bob, and then Alice, I'm going to always measure spin in the x direction, but I'm going to see in my statistics what you're doing on the other side.
Right.
And if you then look carefully at what quantum mechanics predicts, is that what Alice is going to see up or down, it's 50-50, regardless of whether Bob is measuring spin in the x direction or spin in the z direction. So for the statistics, it doesn't matter at all. The story you're going to tell is different depending on whether whether Bob does one measurement or the other measurement. But at the end of the day, for the statistics that you're obtaining in this experiment, it doesn't make a darn bit of difference. And so one way to look upon this is to and this is the viewpoint that I've come to favor. Which is related to this, what is often called the Copenhagen interpretation. It's like, well, one of the things we've learned is that, you can have like these distant correlations that are non-signaling, because like the moment that you can send signals, you run afoul of problems with special relativity, right? So you only want to allow correlations in the world that are non-signaling. And it turns out that class of correlation is bigger than we thought. We thought that any kind of distant correlation, is basically explained by the correlated particles already having the relevant properties the moment they separate, right?
Right.
And it turns out, and this was like the big result of John Bell, like in the early '60s, it's simply impossible to do that. And so, and those proofs have now been simplified to the point that you can explain to a general audience quite simply. So David Merman has done this. I like a book by Tanya and Jeff Boop called Totally Random, like a comic book about quantum mechanics, where they have very simple examples showing how this works. That you get these distant correlations, but you cannot explain those by assuming that everything has already sort of been determined in advance.
Yeah. So one thing that made sort of intuitive sense to me, correct me if this is the right way to think about it. So suppose I have a pair of gloves, a left and the right hand gloves, and I keep the left one in one box and keep the right one in another box, seal them, and I send those two boxes to both sides of the different sides of the universe, right? When I open box number one, I will always find the left glove.
Yes.
And granted, somebody on the other side of the universe is going to find the right glove.
Yeah.
But it doesn't really.
Yeah, that would not surprise anybody, right? I mean, so if only the world were like that. But now the situation is that quantum mechanics says, like, before you open the box, The glove is not left or right. It's only decided the moment you open the box whether
Right.
that glove in that box is left or right, and then it is immediately decided that the glove in the other box has to be the opposite. That is
Okay.
weird, right? And so this is something that Einstein also found. And so Einstein had like so there's a very famous paper that he wrote together with two colleagues, Podolsky and Rosen, called the Einstein-Podolsky-Rosen paper in 1935, which is by now by orders of magnitude Einstein's most cited paper. At the time, it was seen like, oh, the old man has lost touch with physics and all this. Einstein had a simpler argument a year earlier where he says, okay, suppose you have two cups. And quantum mechanics tells you that it's 50-50 which of those two cups have a ball under it. Okay. Now you lift one of those cups and you see, okay, the ball is not under it. So that tells you immediately, well, the ball is under the other cup. Now he asked, well, before I lifted the cup, was it decided that the ball was under the other one? Right. And if you think about it, it's intuitively you would say, of course. But quantum mechanics says no. Quantum mechanics only gives you this probability. And then Einstein says, well, that's too bad for quantum mechanics. Then it's incomplete because, of course, it was known ahead of time, right? And so this then, so he pushed that argument further, in this EPR paper. And then, decades later, with people simplifying that argument, David Bohm, replacing the observables Einstein was talking about by spin components. And then John Bell in the early 60s showing this idea of Einstein that I can just add further description to the quantum system, something called hidden variables, is just not going to work unless, these hidden variables themselves, have very strange properties that they allow, things to travel faster than light, right? Which sort of seems to defeat the purpose. But I mean, this is again, I should not say defeat the purpose. This idea of having what are called non-local hidden variables, such as in the de Broglie-Bohm pilot wave theory, there's plenty of people, especially in philosophy of quantum mechanics, that are quite fond of that way of thinking. And I also know a physicist who like that way of thinking, even though it's sort of in tension. It's not in contradiction, but in tension with relativity.
Okay, so what is the Copenhagen interpretation?
That is a very good question. So this is totally unclear. So so it's the what is typically called the Copenhagen interpretation, or I would call it the mainstream, the textbook interpretation. It's sort of an amalgam of the thinking of Bohr and Heisenberg with a little bit of Dirac, a little bit of von Neumann mixed in. Heisenberg introduced this term at some point way after the fact.
This was a conference where people got together?
No, so the reason it's called the Copenhagen interpretation is just that it's mostly associated with Bohr, and Bohr had this big institute in Copenhagen. That's why it's called the Copenhagen. And so and Bohr, he was kind of a father figure and a guru, a mentor to a lot of these young whippersnappers who put quantum mechanics on the map. The ones that I talked about before, Heisenberg, Pauli, etc. So now, so the
interpretation.
Yeah. So the standard way of thinking about the Copenhagen interpretation is that we're going to need, when you do a measurement, we're talking about sort of the interaction of a quantum system with a classical system. And when you do this measurement, the wave function is going to collapse. That's sort of a very sort of crude sort of physics 101 version of the story. If you look more carefully, you see that that crude view was not held by anybody. But there are there is this idea that when you do a measurement, then one of the possibilities of that quantum mechanics issue is realized, and the others disappear, and that is again in tension with the way things normally evolve in quantum mechanics, which is where you don't have these kind of collapse. So this leads then to something called the measurement problem, where quantum mechanics on this standard account seems to give you one story for, like when things develop left to themselves, and another story for when, like, we as humans like perform like a measurement, right? And so people have felt like, okay, this is just an unacceptable state of affairs, and like have suggested like other ways of making sense of quantum mechanics, such as Bohm or Everett, right? So the Everett interpretation.
So so let me just understand this a little bit better. So before we measure, there is a probability distribution, and at measurement, that probability distribution essentially collapses. And so let me know if I'm thinking this correctly. So let's say I lost my bag in Manhattan, and I say I want to find it, and I haven't looked anywhere. So before I look, there is certain probability distribution the bag could be found anywhere. And I go look in Penn Station, and at that point, it's a 0 or 1. Either I find the bag or I don't find the bag, right? The probability distribution basically collapses at that point. Is that,
well, I mean,
like,
but if you put it that way, right? I mean, there now it sounds like, well, what else is probability distribution supposed to do? Like there's nothing physically collapsing. It's just like, you've now discovered like one of these possibilities is actually correct. Okay. Now in quantum mechanics, it's a little more. It's trickier than that, because you're not discovering, right? To get back to your example of the two gloves, you're not discovering like, okay, here is the left glove is sitting in this box, and therefore the right one in the other box that I've sent to the other side of the universe. No. Quantum mechanics does not allow you to say whether that glove was left or right. Right. So in a way, by doing this measurement, you are like, language becomes like very strained at this point. You are sort of creating, if you wish, like reality. You are forcing, the glove to make up its mind, like either it's going to be like left-handed or right-handed. And this is like, why people are complaining about, like, you shouldn't be thinking about this collapsing of of a probability distribution in the terms of like you finding your lost bag at Central Station. Now, I personally think that this idea that it is not that different from finding the bag at the Central Station, and that what we really discovered is that nature has some intrinsic randomness. Like, at the end of the day, we cannot predict with certainty. Even if we factor in everything we know, there is going to be an intrinsic randomness. Like at the end of the day, the world is the ultimate crapshoot. Okay. People find that like sort of an unappetizing thing to swallow, and this is true for all of these things. So you're a Bohmian, you're a Bohmian. Well, then you have to swallow that like you have an uneasy relationship with relativity theory. You're an Everettian, many worlds interpretation. Well, then you have to swallow that. There's a gazillion copies of you, like in all these other worlds, that you will never have access to, right? So it's one of my
So the Everettian interpretation. So again, going back to the glove example. So the interpretation there is: I open the box, I find a left glove. There is an identical universe where there is a right glove. So everything else in that universe is exactly the same, except the box has a right glove, right? And so both of those happen simultaneously.
So I used to be an Everettian. And so, again, what you're sketching now is sort of the very crude version of Everett. In a way, like it's a little more subtle than that, I think. So basically, right. So the problem here is to explain, like, how is it that these observables, like, at some point acquire like definite values. So in this case, you have a glove. How does it happen that it becomes a left glove or a right glove? Okay. And so, on the Copenhagen interpretation, that, it's just a crapshoot at the end of the day. You do a measurement, you ask nature a question, and then like it makes up its mind, and it's going to be left or right. That's the end of it. Now, on the Everett interpretation, there's never a collapse. All that happens is that you get tight correlations. So quantum mechanics like itself is now going to predict, right, that the moment you open the box, that you enter into a superposition, right? In one, in one part of the superposition says the glove is a left glove, and you believe that it's a left glove. And another part of the superposition is that the glove is a right glove, and you believe that it's a right glove. But this is all like, this may sound strange, but this is a straightforward prediction of the quantum of quantum mechanics. If you believe, which most people do, that quantum mechanics applies to everything, and there's no realm where you have like classical measuring apparatus or anything. Quantum mechanics is the theory of everything. So this now happens. So now you say, but wait a second, but I never am in such a superposition, right? I'm never confused about like whether I'm seeing like a left glove or a right glove. And quantum mechanics again like predicts that, no, you're always going to be sure that you're seeing like a particular thing. So what's going to happen now is that like another aspect of quantum, something called decoherence, is going to ensure that these two terms in the superposition are going to feel like different branches in a multiverse, right? And so that the way to think about this now is that out of this quantum description emerges like one world in which a person very much like you is definitely seeing a left glove, and in another world also like a person also very much like you will see like with the opposite value. I forget what I just said, left or right. And that's so this is like, so I personally when I was still like an Everettian, I sort of prefer to paint this picture not of like sort of a many worlds, but like sort of a one world where everything is perpetually in limbo, and which you can then think of, right, as like different terms in this quantum superposition that all like form like their own worlds, and then quantum mechanics guarantees that none of these worlds will ever know about the existence of any other ones, right? But that's a steep price to pay. Do you really believe that that's the case, right? I mean, like so Everettians have asked me, like Everettians have, like true believers have told me, like whenever I now like narrowly escape disaster, I don't feel so good, because I know that there's many other universes in which like the outcome didn't go so well, right? So there's now many universes in which like I'm living. The two of us are living in a universe where it looks as if like Biden will like like eke out a win, but there's like other universes just like that where like Trump will like.
Don't remind me.
If you're a true believer in Everett, you're going to have to. I mean, a good many branches in the multiverse. Like there are people just like us who are going to live with Donald Trump for 4 more years as president. That's the reality of it.
Yeah, so that's an important distinction. So the superposition is not just for that observation, but it is for anything that is connected to that observation. So in the case of the glove, it's not just the glove, but the observer has to believe it's a left glove, right? And the observer has to be there to believe that. So all the macro systems around that is also in superposition.
Correct. But it's all like you're rapidly now going down what I would call the rabbit hole of the Everett interpretation, which is very popular among physicists. But as I mentioned, like so, I like a few years ago, I sort of fell off the wagon, and by reading another book by the guy I mentioned, Jeff Boop, a book called Bananaworld, Quantum Mechanics for Primates, in which he is like pushing something that now goes by the name of an information-theoretic interpretation, which, as he argues, is really sort of a more reasonable gloss on Everett, right? I mean, all these different interpretations, like, I mean, there are sort of crude versions of it. The crude version of Everett would be like, anytime you do anything, like the world splits into a myriad copies. And I hope to have given you a bit of a sense that that's not fair to the Everettians. Their story is a good deal more sophisticated than that. Also, Copenhagen is a lot more sophisticated than, we posit that there are like big measuring apparatus that is governed by classical physics. No, everything is quantum. But at the end of the day, like you are performing like you are performing experiments, and like these experiments like have like random outcomes. And what's worse, and this to me from this information theoretic perspective is really sort of the weird thing about and the new thing about quantum mechanics is that if you now want to know two different properties of like a system, you cannot like typically you cannot find that out at the same time. So suppose to stick with your glove example, that you not only want to find out whether they're like right-handed or left-handed, but whether they're black or brown. All right. So classically, you think, oh, this is no problem. I can check whether it's left or right, and I can check whether they're black or brown. But in quantum mechanics, you can't do this. Like these properties are represented by mathematical gadgets that prevent you from doing that. So you end up with your picture of the world is going to depend heavily on what you decide to do. If you decide to look at, okay, is this left-handed or right-handed, you cannot at the same time like have a picture in which like it's like black or white, and all these pictures just don't add up to one overall big picture. So this goes by the technical term of you don't have like an overarching Boolean algebra, where Boolean algebra is just like a fancy way of saying you assign like yes, no, yes, you assign true false values to every statement you care about. So if you care about the statement, is the glove is black, yes or no, right? You cannot in the same world like assign a value yes, no to the glove is like right-handed, left-handed. Right now, this is like a very unusual and hard to get used to property. But so people in this camp, right, to which I now count myself, are saying, okay, that's what we've learned. Like it turns out to be possible to have experience of a world like that. And what we then see, like all the other guys are doing, are like desperately cling to this idea that no, there has to be like one overarching thing that in which it all makes sense, be it a multiverse or be it like non-local hidden variables, right? That's the Bohm or the Everett way. And we're saying the way that we're reading Bohr is Bohr saying that's the sort of stuff that you have to give up. Let that go, and then just accept what you've discovered here about quantum mechanics. And so you mentioned at the beginning this book that I wrote, understanding quantum Raffles. And that's precisely the sort of view that we are arguing for. And basically take the attitude like, look, the things like the measurement problem. At the end of the day, like we don't see this as problems. We just see this as sort of features of reality that we've discovered, and that you just need to accept, right? And this is very close to what the leaders of this Copenhagen movement, like the mainstream, like the Pauli, Heisenberg, and Bohr were saying.
Right. So are you saying then, Michel, that the paradox arises from really sort of counterintuitive? We didn't have quantum mechanics for most of human history. We didn't, go out to kill and eat. We didn't really have thought experiments about quantum mechanics. And we very recently found this. And so our brains are not really designed for this concept. And so every time we think about this, we are going back and testing, based on our sort of natural understanding, and it's all counterintuitive.
No, I mean, so this is like, that sort of goes back to something I said about like the history of the subject. I mean, if it weren't for like these unbelievably puzzling experimental facts, in particular in spectroscopy, that came to light, like in around 1920 or so, we would never have gotten to a theory this weird. But now we do, and we know, like from using it now for a century in physics, this theory works. Where classical theory really didn't, And so now, like, the question is like, okay, how do you make sense of this? And like, so there's like various options on the table, and no matter what option you go for, like, a colleague of mine in Minnesota calls it the conservation of misery. That no matter what option you're going to go for, you're going to have to swallow something that is kind of difficult to swallow. So, do you really believe that that we're living in a multiverse? Do you really believe that maybe special relativity is wrong? And so yeah, this is where we're at, and everybody. And I don't think a part of it is that there are just no knockdown arguments, right? I mean, like, it's not as if like, we can do this calculation and now we can show like this position is inconsistent. At the end of the day, it's like plausibility argument.
And it may not be testable, right?
But
that is
there's
that
also
is
like,
issue.
I mean, I would be remiss if I did not mention this. There's also like one interpretation is on the table, which actually changes quantum mechanics. So the interpretation I've talked about so far, Copenhagen, Everett, Bohm, they don't want to change quantum mechanics. Bohm wants to add something to it. Bohr and Everett want to try to add nothing to it. Like, they smuggle some things in, but they try. But there's another approach called the GRW approach, called for Girardi, Remeni, and Weber. They want to change like one of the central equations of quantum mechanics, the Schrödinger equation, and have like a little stochastic terms where that work out in such a way that if you go to large enough systems, say cats, that they will collapse so that you don't have the embarrassment of like cats that are in a superposition of being dead and alive, okay? Or gloves that are in a superposition of being left and right, or black and brown. So, but this is really changing, small change in quantum mechanics. And so in principle, such a theory might be testable, as long as it's not testable. It's just, I would say, it falls in with all these other theories. Like, well, okay, if it makes you feel better to like add this little wheel to the operation, fine. But these people could claim like, no, we're not adding like another epicycle to the system. We are like changing the theory in ways that maybe we can predict. It's not going to be totally random. We're going to come up with some other like sort of statistical regularity that hinges on the details of how we add this stochastic like collapse mechanism.
Right. So in conclusion, then, Michel, give me sort of your interpretation of it, or your preference.
Yeah. So I've already sort of indicated what my preference is, right? And so now, and I think the best, if you give me you're basically giving me a chance to put in a plug for my point of view, right? And so rather than reiterating what my point of view is, I would say this. So what I see as the strongest argument for the kind of view I'm pushing, and this is like what a lot of our book is about. It turns out that the central formalism of quantum mechanics, the Hilbert space formalism that was introduced by von Neumann, is the exact same formalism that is used in sophisticated modern treatments of statistics and probability theory. Okay, and so what that seems to tell me is that Hilbert space is not something about like the furniture of the world. The world is not made out of wave functions, as Sean Carroll says in his new book. No, Hilbert space is like a formalism to deal with probabilities, right? And so if you from that point of view, I think you can sort of work out like a consistent way of thinking about quantum mechanics that sort of avoids like these big problems, the measurement problem in particular, right? Where you have to swallow some other things, like, there is no overall Boolean description. No, we cannot completely write the observer out of the story, right? These are like, big concessions to make. But to me, like, given this close parallel between general probability theory and like the Hilbert space formalism of quantum mechanics, that seems to be the most promising avenue to me to have an interpretation.
Great. This is exciting. The thought experiments one could do here would keep you awake.
I mean, the other thing I should really say is that these are not thought experiments anymore, right? I mean, so ever since the late 60s and early 70s, these experiments that for Einstein were thought experiments have been done. So there are all these experimental tests of the Bell inequalities. They're ongoing, and again they find that quantum mechanics is correct. And so yes, the spooky action at the distance that Einstein was talking about, that has been proven. Right? And you can, and the other thing I'll mention is that no matter how you think about this, I mean, since it's there, you can start thinking about what can we do with it, right? And so now you have like quantum computing, quantum cryptography, and even though the debate about how to make sense of this like rages on, that's not going to stop quantum computer engineers from trying to come up with like physical systems that could actually realize some of the computational power that would come with exploiting these new options.
Excellent. Yeah. This has been great, Michel.
My pleasure.
Thanks so much for spending time with me. And
right.
Thank you.
This is a Scientific Sense podcast providing unscripted conversations with leading academics and researchers on a variety of topics. If you'd like to sponsor this podcast, please reach out to info@scientificsense.com.